In this video, we'll introduce some additional ways of finding subgroups in a group. That is the center, centralizer, and normalizer. So I'll start with the center of a group G, which is denoted ZG. I think it's because it comes from German originally. The center of a group is the set of all the elements in the group that commute with every element of G. So let's just give some examples to see what this looks like. So ZG is the whole group if and only if G is abelian. Right? I mean, any two elements in a group commute if and only if the group is abelian. So if the group is not abelian, you can find some pair of elements AB where AB is not equal to BA. So that means that A and B both can't be in the center. Okay. Here's a group that we talked about last time, the quaternion group of order 8. So remember, that's 1 minus 1, I minus I, j minus j, and k minus k. And the center always includes the identity, but here it also includes minus 1, right? Because minus 1 times any other element is equal to the same thing as that element times minus 1. Okay, what about Sn? Well, it's a little exercise to show that the center of Sn is trivial as long as n is greater than or equal to 3. S2 is just the same thing as Z mod 2Z. It's a group of two elements and they're all the same. But as soon as you have at least 3 elements, the center of Sn is trivial. So given any permutation, you want to find another permutation that does not commute with it. And this is a good exercise to do. Okay, here's another good exercise to do. So let's take GLN-R, n by n invertible matrices with entries in R. The center is, well, one set of matrices that commutes with all other matrices is the set of diagonal matrices, right? Like not just multiples of the identity, but any diagonal matrix. And so it's not hard to see that those are in the center. It's more difficult to show that that is the entire center. That if you have a matrix that's not a diagonal matrix, you can write down another invertible matrix that it does not commute with. So, okay, so it's the set of n by n invertible diagonal matrices, which just means that every diagonal entry is non-zero. So again, that's a good exercise to do. Okay. So in all of these examples, we see that the center is a subgroup of G. It's not hard to see that the set of diagonal matrices is a subgroup. Invertible diagonal matrices is a subgroup of GLN-R. And this is a general phenomenon that for any group G, the center is a subgroup. And rather than prove this, I'll say that it's a special case of a more general construction. So let's define the centralizer of a subset. So let's say that A is a subset of G. The centralizer of A in G is the set of all elements of G that commute with everything in A. Okay, so we can write that another way. And I'll also give you the notation. So we usually write C, G, A is the set of all G in G, such that you could write GA equals AG, but maybe instead it's a little nicer to write G A G inverse equals A for all A in A. So I'll pause and erase, and I'll talk a little bit more about centralizers. The centralizer of a subset A and G is the set of all elements that commute with everything in A, which is the same as saying it's the set of all elements of G, so that G inverse equals A for all little a in the set A. Okay, so first note, if you let A be the entire group G, then you're asking for the set of all elements of G that commute with every element of G, and that is the definition of the center. Okay, so I said that the center of a group is a subgroup. That's one instance of this more general fact that for any subset A, the centralizer of that subset is a subgroup of G. Okay, so let me say something about the proof. So this is on page 49 in section 2.2 of Dummett and Foote. So first, we want to show something as a subgroup. So how do we do that? The subgroup criterion. So first we need to just note that the centralizer is not empty. And why is the identity in the centralizer? Because, well, what does it mean for the identity to be in here? So let me just write, because 1A, 1 inverse is just A for all, not just A and A, but for any A and G. So this is always true. The identity element always commutes with every other element. All right, so now how are we going to do the rest of this proof? Is with the subgroup criterion. So what do we need to show? So we're going to show that if X and Y are in C, G, A, then XY inverse is in C, G, A. Okay, so what do we know? So we know that X, A, X inverse equals A for all elements in your set. And we know, same thing, Y, A, Y inverse equals A for all A in your set. And the idea is we're going to multiply this second expression by Y inverse on the left and Y on the right. And that's going to tell us that A is Y inverse A, Y for all A in A. So it's the same thing except we've like switched Y and Y inverse. So now we're going to take this expression and multiply by X on the left and X inverse on the right. So where does that leave us? We're at X, A, X inverse equals X, Y inverse, A, Y, X inverse, X, A, X inverse. That's equal to A. So this almost looks like the kind of thing that you need to be in the centralizer. So we just need to note that what is YX inverse? This thing on the right-hand side, this is equal to XY inverse inverse. That you can check that if you have YX inverse and you multiply by XY inverse, the X's cancel, the Y's cancel, and you get the identity. So what is this? So this is XY inverse A, XY inverse inverse, and now we are done by the subgroup criterion. So XY inverse is in C, G, A. So I wanted to go through this argument because it's a sort of nice application of using exactly what the subgroup criterion says to show that something is a subgroup. So I'll pause and erase, and then we'll talk about a slightly different idea of finding subgroups within a group, which is instead of taking a centralizer, taking a normalizer. Before moving on, I want to emphasize that this idea that came up when talking about centralizers of looking at an element A and then looking at GAG inverse is very important. This is going to come up again and again throughout this course. Sometimes we say that GAG inverse is the conjugate of A by the element G. Or this operation that we're doing is called conjugation by G. Okay, so instead of asking for the set of all the elements in G that commute with every element of A, we could instead take only the elements that commute with A as a set. Okay, what does that mean? We want elements G where G times the set A is the same as A times the set G. So what is this G times the set A? It's the set of all the elements little g times little a, where little g is some fixed element, and A goes through the elements of your set. Same thing over here. It's the set of all elements little a times this fixed element G, where A goes through the elements of your set. So the set of things that you get by taking G and multiplying by elements of A on the right is the same as the set of elements that you get by taking little g and multiplying by elements of A on the left. I'm definitely not saying that G times little a has to be equal to little a times G for any particular elements A. It's just when you go through everything in the set GA and the set AG are the same. Okay, so the normalizer of A in G is the set of all elements in G so that GAG inverse equals A. And you can see that GAG inverse equals A is the same condition as GA equals AG. Okay, so first, I just want to note that clearly the centralizer, which asks for elements that commute with every element in the set A, is a subset of the normalizer, which asks for elements where GA equals AG for the whole set. But they don't have to be necessarily equal. So let me give you an example. So if we take G equals S3, and we take A to be the identity permutation, the cycle 1, 2, 3, and the cycle 1, 3, 2. What is the centralizer? CGA equals A. So it's not hard to see that these three elements form a subgroup. That group is abelian, like 1, 2, 3 times 1, 3, 2 is the same as 1, 3, 2 times 1, 2, 3. Maybe one nice way to say it is that 1, 2, 3, 2 is the cycle 1, 2, 3 squared. And a cyclic subgroup is always abelian. So what else do we need to say? We need to say that if you take another element that's not in this set, any one of the other three transpositions, it does not commute with all of the things in A. Okay, and then what is the normalizer? It's the whole group. So how do you see that? Well, let's just show that some elements, so clearly the elements of A are in the normalizer because they're already in the centralizer. But let's just give an example. We want to show that like 1, 2, 1, 2, the transposition times the set A times 1, 2 inverse is equal to the set A. So first, 1, 2 inverse is 1, 2. A transposition is its own inverse. You flip 1 and 2, you leave 3 fixed. You flip them back, and you're back at the identity. So what is this set of elements? Well, we have 1, 2 times the identity times 1, 2 is just the identity. Then we have 1, 2 times 1, 2, 3. 1, 2, 3. 1, 2. And then we have one more element. What is this? Well, 1 goes to 2, 2 goes to 3. So 1 goes to 3 and then stays there. 2 goes to 1, 1 goes to 2, 2 goes to 1. So 2 goes to 1. 3 doesn't go anywhere. 3 goes to 1, 1 goes to 2. So this is equal to 1, 3, 2. And now I'm out of space, but you'll see that if you take 1, 2 times 1, 3, 2 times 1, 2, you'll get back the permutation 1, 2, 3. So this set is equal to the set A, and the element 1, 2 is in the normalizer. So I'm going to pause and erase, and then we'll talk a little bit more about the normalizer, and then we'll explain why it's called that. I wanted to first just take the example that we just did and write it up a little more clearly. So you have G is S3, A is this cyclic subgroup of size 3. We see that the centralizer is A itself, and the normalizer is the whole group. Well, how do you see the normalizer as the whole group? Well, take some element not an A, like 1, 2, and just compute what is 1, 2, A, 1, 2 inverse. That's 1, 2, A, 1, 2. So that's the set of 3 permutations. 1, 2 identity, 1, 2 is just the identity. 1, 2, 1, 2, 3, 1, 2, 1, 2, 1, 3, 2, 1, 2. And that's the identity 1, 3, 2, and 1, 2, 3. This conjugation operation has switched the last 2 elements of the set A, but as a set, it's still true that 1, 2, A, 1, 2 inverse is the same as A. So 1, 2 is in the normalizer. Same thing is true for any of the other 2 transpositions. Okay, why are we talking about normalizers? Well, the normalizer of a subset is also a subgroup. And the proof is very, very similar to the proof that the centralizer of a subset is a subgroup. So I'll leave the details as an exercise. All right, so now we get to one of the really big definitions in group theory. A subgroup H is called normal. And we write it with this H triangle with a line under it. If G times the subgroup H times G inverse is equal to H for all G in G. So you take the subgroup H, you conjugate by an element G, you look at the set of elements that you get. If you always get back H, then your subgroup is normal. Equivalently, and it's a nice exercise, you should check the details, that this is really equivalent to G times H being equal to H times G for all elements G. So now this one is a little less clear. It's enough to check if you want to say that GH G inverse is equal to H for all G. It's enough that GH G inverse is contained in H for all G. So there are several equivalent conditions to being normal that are described in Theorem 6 of Dummett and Foote on page 82. And I'm not going to go through all of those equivalent conditions, but I encourage you to read it and write out full proofs for yourself. Let's look at some examples of subgroups and ask whether they're normal or not normal. So first, if G is abelian, then every subgroup is normal, because whenever you take G times any element, little h, times G inverse, you can just switch the order of little h and G inverse to cancel out the G and the G inverse. So the conjugate of every element is that element itself. So of course the set GH G inverse is the same as the set H because the elements match up in a one-to-one way. So nothing interesting is happening for abelian groups. For non-abelian groups, it's much less clear when you take a subgroup whether or not it's normal. So not every subgroup is normal. Let's see an example. Let's take D6 and take H to be the subgroup generated by one of the reflections. So what is R, H, R inverse, where R is one of the rotations, an element of order 3? Well, okay, so this is R, ID, the trivial elements. Let me write R1, R inverse. And then we have RS, R inverse. And okay, so this first element is just 1. And this next element, well, what is SR inverse? This is RS. So this is the same as R squared S, or you could write this as SR. And the point is this is not the same as S. So this is not the same as the subgroup generated by S that we started with. So because we found an element G in G so that G, H, G inverse is not equal to H, this means H is not normal. Okay, so why is normal so important? Why is this something that I'm emphasizing here? And in the short term, the biggest reason is because of the study of quotient groups. Normal subgroups are going to play a really big role. So quotient groups. And what is the idea behind a quotient group is we take some group, we take a subgroup, and we're going to make new groups out of our pair of a group G and a special kind of subgroup K. So make new groups from old. Why else is the idea of a normal subgroup so important? Well, I'll motivate this with another definition. A group G is called simple if it has no proper non-trivial normal subgroups. So a proper subgroup is just any subgroup that's not the whole group G, and a subgroup is non-trivial if it's not the trivial subgroup, just the identity. So Z mod PZ is simple. Well, last time we saw that Z mod NZ, that's a cyclic group, and the subgroups of a cyclic group are all cyclic. If you have Z mod NZ, then the subgroups are in bijection with divisors D of n. So if n is prime, then the only divisors are 1 and the prime itself, and the subgroups you get out of that are the whole group and the trivial subgroup. So that means this group is simple because not only does it have no proper non-trivial normal subgroups, the reason is that it has no proper non-trivial subgroups at all. Okay, so why do simple groups matter? In some sense that we'll talk about a little bit later, simple groups are like building blocks of all groups, or at least all finite groups. So simplicity is an important property of groups that will come up several more times throughout the course.